In this video, we're going to talk about the general ideas behind second-order non-homogeneous linear equations and how we go about trying to solve them. So if we're looking at a non-homogeneous second-order linear equation, the most general form is given here, where you have your y double prime term, you have your y prime with a p of t attached to it, your y with the other function q of t on it, and then the g of t here on the right-hand side. The key for this being non-homogeneous is that this g of t over here is non-zero. So the question really comes down to, how does that change what our solutions look like? We have a pretty good idea theory-wise what our solutions always look like for homogeneous equations. The question is, how does that change if I make it non-homogeneous? Just a refresher, for homogeneous, we know we're always going to get something with a form c1 y1 of t plus c2 y2 of t, and that's always what this solution looks like in any case. If it was constant coefficient and stuff, we could then solve for this y1 and y2 are. But even if we can't solve what they are, we know that in theory, because it's a linear equation, superposition holds true. We're always going to get a solution that has this sort of structure to it, c1 y1 plus c2 y2, when we have a homogeneous problem. So what happens if we add a g of t on the other side? Well, how can we try to solve these? Well, the idea sort of comes down to, is there a way that I can go back from the non-homogeneous problem into a homogeneous one, because that second one I know how to solve. And so let's look at what we've got. So if we've got, our non-homogeneous equation like this, I want to somehow get this g of t to be 0, because if I do that, I know how to solve that problem. And the key thing that's going to help us here is the fact that we are starting with a linear equation, and so all of our linearity principles hold. The key point here will end up being superposition. So we're going to let u1 and u2 be two solutions to this non-homogeneous problem. What that means is then that u1 double prime plus p of t u1 prime plus q of t u1 equals g of t. Also going to correct myself, there should not be a prime on this exponent up here. And similarly for u2. Now, I want to get to a 0 on the right-hand side, so let's subtract these two equations and see what happens. Well, if I subtract those two, I then get the following. I get u1 double prime minus u2 double prime plus p of t times, factoring that out, u1 prime minus u2 prime plus q of t, factoring out u1 minus u2, equals 0 because I did g of t minus g of t on the right-hand side. And what do I notice here? Well, the derivative is linear, which means that u1 prime minus u2 prime is just u1 minus u2 prime. And the same goes for second derivatives. This becomes here u1 minus u2 double prime plus p of t u1 minus u2 prime plus q of t u1 minus u2 equals 0, or by rewriting v as u1 minus u2, what I see here is v double prime plus p of t v prime plus q of t v equals 0. If we scroll back up, that is exactly the first equation I started with, replacing that g of t by a 0. So by taking two solutions and subtracting them, I have gone from the non-homogeneous problem back to the homogeneous problem. Okay, that was a fun little trick, but why is that useful to us? Well, it's useful because then we can think about this, instead of saying u1 minus u2 is v, we can think about this instead as u2 being u1 plus v. And the benefit here is, theoretically, I know how to find v, because v comes from a homogeneous problem that I potentially know how to solve. So restructuring this into a sort of a statement of a theorem here, we have the following. If u1 and u2 are two solutions to the non-homogeneous problem, y double prime plus t of ty prime plus q of ty equals g of t, the difference, v, which is u1 minus u2, solves the corresponding homogeneous problem where I've gotten rid of the right-hand side. Now, this works in theory no matter what sort of problems we're trying to solve. However, let's now assume that we're in the constant coefficient case, where p and q are both just constants. Then what happens? Well, then I know what the general solution to the homogeneous problem is. It's c1 y1 plus c2 y2, and I know how to find that y1 and y2. So what that means is that I know what this v has to look like. I know that v is going to be c1y1 plus c2y2, and I know how to find these functions. Now, how do I tie this back to the non-homogeneous problem? Well, that means that I know for that problem, I know that u1 and u2 differ by this function v, or I know that u2 is going to be u1 plus v. This holds for any u1 and u2 that solve the non-homogeneous problem. This means that if I fix u1, I can get to any other u2, any other solution of the non-homogeneous problem, just by adding a solution to the homogeneous problem that I know how to find. And so to get to any solution, we're going to look at this thing being our sort of general or any solution to the non-homogeneous problem. I have to pick something that solves the non-homogeneous problem and then add the general solution to the homogeneous problem. So this will be something that solves the non-homogeneous problem, and then you're adding to that the general solution of the homogeneous problem. So the little terminology that you'll see in other places that you might get used every now and again. So this one thing that solves the non-homogeneous problem is often called the particular solution and denoted y sub p. The solution to the homogeneous problem in this case is often called the complementary solution and denoted y sub c. What this leads us to is that we only need to find one thing, this y sub p, that solves the non-homogeneous problem. Once we do that, the general solution to any linear non-homogeneous second order problem will be y equals that yp plus yc, my complementary solution, or writing that out in more detail, it will be yp plus c1y1 plus c2y2, where the y1 and y2 are the linearly independent solutions of the homogeneous problem. Again, if it's constant coefficient, we know how to solve those. Otherwise, they would have to be there for you. And so this is how we're going to go about solving these kinds of problems. We can solve the homogeneous part, and then we just have to find the one thing that solves the non-homogeneous problem. And we'll have a couple different techniques that we'll discuss going forward with ways that we can go about trying to find this y sub p for a given constant coefficient non-homogeneous second order problem.